Welcome back to the second part of covariance, and this is properties of covariance and variance. And the first is what we had mentioned at the beginning of the last video, and that is the covariance of x with itself is the same thing as the variance of x. The definition, the covariance of x and y is, the definition is the expected value of x minus mu sub x times y minus mu sub y. And if you plug in x for the y values, then you get the expected value of x minus mu sub x squared, which is the variance. So that we saw the last time. Now, here are some other properties that we have not seen before. Next, property number 2, the covariance of a times x plus b times y. A times x, b times y, these are real numbers. A, b are just real numbers, is equal to ab times the covariance of xy. And so here we are using the computational formula of the covariance. The covariance of xy is the expected value of x times y minus the expected value of x times the expected value of y. If we use that formula here, plugging in ax for the x, by for the y in the computational formula, doing it in both places, linearity of the expected value says that I can pull the constants outside of the expected value, and I can do that in all cases. So I'm getting AB times the expected value of xy minus AB e of x e of y. Factor out the AB. Here is the computational formula of the covariance, and it is as simple as that. Now, what does this have? What is the implication on the variance? Well, the variance of AX, well, that's the covariance of AX times, not times, covariance of AX with AX, right? That is this result here. The variance is the covariance of the variable twice. Pulling both of these out as in the previous, right? Pulling both these out as in the previous with the correlation here, that gives me A times A, or A squared times the covariance of XX, which is A squared times V of X. So there is the analogous property with the variance. Next, the covariance of a sum with constants. So here again, number 3, here again we are talking about B and D as constants, just real numbers. Moving x, a translation of x plus b, and a translation of y plus d affects the relationship between them not at all, is equal to the covariance of x and y. And so the proof is outlined, well, no, it's not outlined. The whole proof is sitting right here. And so what do? Well, you use the computational formula again, plugging in x plus b for the x value, y plus d for the y, and in both cases, and then my friends, you just crunch it all through. So you FOIL through within the bracket and you get the expected value of all this. Inside here, you're using the linearity of the expected value and the fact that the expected value of a constant is a constant. So you get, for the expected value of x plus b, you get expected value of x plus b, and the analogous result for y. Now, again, the linearity, the expected value distributes over each of those terms. Constants come out, and the expected value of a constant is a constant. We're using just those same properties of linearity. Here we are foiling, right? We're multiplying, we're expanding that through to get this lovely result, because these terms cancel out. Those terms cancel out. Everything cancels except e of xy and e of x times e of y, which just so happens to be the covariance computational formula. So shifting variables does not affect the relationship, the covariance between them. And what does that mean for the variance? Well, the variance, if you run through the same computation with x plus b and x plus b as both entries, well, you're just going to find that shifting a single variable doesn't make any difference to its variance, and that makes perfect sense. That makes perfect sense. If you look at a standard normal, or any distribution for that matter, if you look for a standard normal and you just take it, if this is z, and we shift z over to z plus b, right? So we move over to some point here, b, and we've got our normal around b now instead. Does that change anything about the variance or standard deviation, the width of the curve? No. No, it doesn't. So graphically, that is what this result is telling us with the variance. And the covariance relationship is sort of analogous, although the covariance is obviously measuring a relationship between x and y. 2 and 3 can be stated together. 2 and 3 can be stated together typically. So the covariance of ax plus b, cx plus d is, well, the b and the d don't change anything, and the a and the c come out, and so they're very often stated together as a single property here as this. And similarly for the variance, as a single property, 2 and 3 are the variance of ax plus b is a squared times the variance of x. Nextly, we have what is called semilinearity for the covariance. The covariance of x plus z and y is the covariance of x and y and the covariance of z and y. And there's nothing special about the first variable here. It could have been the covariance of x and y plus w. It's the covariance of x and y plus the covariance of x and w. And what is really nice about this is that it looks like, well, it kind of looks like you're foiling, but we'll see that more in just a second. So if we run through this proof, again, it's just the computational formula. It's just the computational formula. If you distribute within the brackets and you distribute the expected value, and then you distribute again, and distribute the expected value again, then you can group terms together. The terms grouped in red turn out to be exactly the covariance of xy. The terms grouped in blue turned out to be exactly the covariance of zy, and there is your proof. So putting this together with a whole linear combination, if we use this property above, and split it up first of all on the x's, right? If we split it up on the x's, then we get the covariance of ax with the second piece and bz with the second piece. Now if we split it up using the analogous result over here, then we get these pieces broken into two, and it looks like here as well the constants all come out, right? The constants all come out, and you end up with this as your final result, which is super easy to remember because it is every single possible pairing, and it looks like foiling. It looks like you're expanding. That is not what you're actually doing, but it looks like you're expanding, right? If you were multiplying these things, you'd have axcy, and here you've got the a times c times the covariance of xy. It looks, right, like an expanding here. Ax dw, so a and d come out, covariance of x and w, and so on and so forth. It really, as a memory aid, you can imagine that you are foiling these through, and instead of multiplying, you're taking covariances, and that will work for you, giving this sort of expansion property of the covariance. And what does that mean for the variance? Well, the variance, this is actually quite a well-used little formula. It is just the consequence of what is above, but as its own formula, it is often sort of given as the relationship between the relationship of, let me try that again, of the variance of a linear combination of random variables. So here, the variance, again, is the covariance with the term repeated. If you apply this result, and simply recopy the x and the y where they belong in this expansion up here, you will get this. And the first term, a times a gives us a squared. The covariance of xx gives us v sub x. On the other end, we have b times b and the covariance of y with itself, which gives us b squared times the variance of y. And then what we have in the middle, right, which is like the cross terms, this kind of looks like you're squaring, right? If the above term is foiling, then this is sort of like squaring. Obviously, we're not actually multiplying here, but it's a good sort of memory aid. It looks like the squaring formula that you've known since high school. Then these two terms, the covariance of x, y, is the same as the covariance of y, x, and so you get 2ab times the covariance of x, y. Now this extends to multiple variables. If we have every single possible pairing of a covariance of linear combinations, right? So we had two little ones here, ax plus bz, cy plus dw. Here, if we have a linear combination of n variables and a linear combination of m variables, and we want to expand using every single possible pairing, well, the way to do that succinctly is with a double sum, right? I from 1 to n captures all of the x variables. J from 1 to m carries all of the y variables. And then we have every single possible pairing adding all of these up. If we apply this to variance, well, you are getting the same expansion here, right? The same expansion, except that some of these terms, when the xi lines up with the xi, then you are getting variance, right? So sometimes this is stated with a variance terms, but this is exactly the same expansion here. But in particular, if the xi's are mutually independent, then when you have an xi, the covariance of xi with xj, when I is not equal to j, if they are mutually independent, they are uncorrelated, and if they are uncorrelated, that covariance is 0. So all of these terms, they're called cross terms when I is not equal to j, they drop out. And all you are left with is the terms when I is equal to j, in other words, the covariance of xi, and that is the variance. So in the very special case that we have independent random variables and we're taking a linear combination, then this is what you get for the variance. But in general, you don't get to drop out the cross terms, and so you've got this big double sum of all possible pairings, and that is just a special case of this. Excuse me, expansion of the covariance. So let us look here at a couple of examples. So let us calculate, first of all, here we've got x and y are jointly distributed with density function given here over this rectangle. We are looking to calculate the variance of w, where w is, well, it's the average of x and y, isn't it? It's 1/2 x plus y. We're going to do this in two ways. The first way we're going to do using the variance formula. And the second way that we're going to do it is by using this covariance expansion that we have just talked about here. So using this formula, using this first formula here, the variance formula, E of W is the expected value of, well, W is 1/2 x plus y, is if we use Lotus and just put in our function x plus y, again, I have skipped the evaluation step because this is a double integral that we know how to do, but it would involve expanding these two terms and computing the double integral. We're going to get 7/6. E of W squared is the expected value of W squared, which is the expected value of 1/4 x plus y squared, which means that in Lotus, x plus y squared is going to go in front. Now, obviously, this is an integral. We'd have to expand this whole big term here to compute this, but if we did, we would get 3/2 as a simple answer. And then using the variance of W, using the variance formula, we would have E of W squared minus E of W all squared, and we'd get the answer of 5/36. That should be the exact same answer that we get if we do the formula that we have above here, if we have the formula that we have above. So using the variance formula, in fact, we are using this one. We are using the variance of the simplified version, AX, and no, we are not doing that. We are using AX plus BY, and that is A squared times the variance of X plus B squared times the variance of Y plus 2AB times the covariance of XY. And so if we use this formula and we first bring out, right, the 1/4, in our case here, both A and B are 1/2, and so we bring those out squared, and we factor them out here, and then we have this formula for the variance. If we apply this, we should get exactly the same answer. So calculating this requires more little pieces, but requires a whole lot less expansion that we didn't actually do here because I skipped those steps. But there is quite a lot of algebra. There's quite a lot of algebra here that was skipped over. So although it seems like there's more integration going on, the integrals are all simpler in this formula. So first of all, we need E of X and E of X squared. Plug in X squared into the formula, integrate, and there you go. If you look at the density function is absolutely symmetric. The rectangle has the same size from 0 to 2, If you interchanged X and Y, you would not be able to tell. And so by symmetry, you are going to get the same values for E of Y and E of Y squared. Now, we need one more little integral to do here, and that is E of XY. Again, using Lotus, xy goes in as the function, and we integrate, and we're going to get this value of 4/3. Then, to put everything together here to use the expanded formula of the variance of a linear combination, we need the variance of x, which incidentally, also because of symmetry, is the variance of y. If we calculate that, E of X squared minus E of X all squared, we're going to get 11/36. The covariance is E of XY minus E of X times E of Y. That is what's going on here, and we get this value minus 1/36. Plug that all into this formula up here, and you will see that you do, in fact, get that same answer as 5/36. So two different ways of calculating it. As far as the efficiency of it, I would say if you were actually doing it by hand, this way would probably be a little bit quicker because the algebra here is simpler than the algebra you would need through all of this expansion up here. Right? There's 2 integrals here. Down here we had to do 3 integrals, but they were simpler. One last example here. Let us say that x and y are random variables such that we have their expected value and their second moments, as well as the expected value of xy. Let them also be such that w, which is their sum, is known to be normal. then we are asked to find the probability that W is greater than 5. So if W is known to be normal, to calculate probabilities, we need to know its mean and its standard deviation. Well, that's its variance, but we need to take its square root after. So the mean of W is the expected value of W is the expected value of x plus y. Using linearity, that just gives me 3. Now, the sigma squared, the variance of x plus y, is a little bit more complicated because these are not independent variables. And so if they have a covariance value which is non-zero, then we have to use this formula. If they did, well, if they had a covariance value which was 0, that term would go away, but it doesn't, right? It doesn't. So, well, we don't know it doesn't, but we have to assume that it doesn't until we show otherwise. So if we calculate all of these, the variance is e of x squared minus e of x all squared. Variance of y, e of y squared minus e of y all squared, plus 2 times the covariance, e of xy minus e of x times e of y. Plugging in those values, here's the covariance. You see you get a value of 2, and so that value cannot be ignored. There is the variance, and so if we're looking for the standard deviation, we're looking for the square root of the variance, or root 7, which is approximately 2.65. Now we have everything that we need. If W is a normal random variable with the mean of 3 and the standard deviation of root 7, well then calculating W is greater than 5 is a plain old normal calculation. So using the complement rule, that's the probability that W is less than 1 minus the probability that W is less than or equal to 5, which translated into a standard normal is the probability that Z is less than 5 minus 3 over root 7. Plugging that into the normal CDF, and you will get this value here for W. Now, I cannot emphasize enough that unless you know otherwise, unless you know that variables are uncorrelated or independent, which implies that they are uncorrelated, then you cannot ignore their covariance. And if you need to calculate anything about their sums or their linear combinations, then you must use the appropriate covariance formulas.